in the second session of the FDP. Soon we shall start. I am waiting for the speaker. Maybe he has, yes, he is joining. So we shall start maybe. So please bear with us. Hello, Professor Thakur. Can you unmute your microphone?
Hi.
Yes.
I think, am I audible?
Yes, yes, yes. Okay.
Yeah, okay. So I would just like to share the screen and kind of start the session.
Okay, just let me a small introduction, then we shall start.
Yeah.
Okay. So now we are going to start our second session, and our resource person is Professor Ajay D. Thakur from Department of Physics, IIT Patna. He will be speaking on advancements in bolometry from superconducting transition edge sensors to thermoelectric membranes. Professor Ajay D. Thakur is working in the Department of Physics at the Indian Institute of Technology, Patna. Main research interests of his group are physics, motivated exploration of sustainable functional materials and technologies. Professor Thakur implemented 4 major research projects at IIT Patna. He has published more than 86 research papers in peer-reviewed international journals and delivered more than 40 invited talks in seminar, conference, etc. He has guided several PhD students, and several of them are working under his supervision. Professor Thakur has active collaboration with various research groups in India and abroad. So I welcome Professor Thakur and thanks for accepting our request to deliver a talk during this program. So I request Professor Thakur to start his lecture. Sir, please.
Thank you, Professor Hussain, for a kind introduction. I am really sorry I was asked to send some document related to this. I forgot. It completely skipped my mind. So I think you would have made it from other sources. So I apologize for that. So let me just start the discussion. This is a development program. One of the interesting sensors that people have been using for studying a large class of physical problems has been bolometry. Right. So bolometry, to begin with, had its origin in astronomy. So where a scientist named Langley, he invented bolometer in early, I think, 19th century. And what we are going to look at today is try to understand what meters are and how like superconducting transition edge sensors or thermoelectric membranes can also act as bolometers. So bolometers per se have been really like materials which were metals or semiconductors to begin with, and of late people have been trying to make bolometers out of a variety of other platforms. So just to ensure that this talk also has pedagogic content, I have decided to initially go ahead with slides as mentioned in the outline. So we'll start with how bolometers work, how people have tried to enhance their performance, some related work from our group where we have tried to develop metal systems which may have bolometric applications. And then I would go into a kind of blackboard type of a discussion on equivalent circuit of a superconducting bolometer. Why this is required is because once I introduce bolometers to you, it is very easy to access the latest literature and try to go through all kinds of developments which are going in this area. However, like it becomes very important to do something like at the level of a textbook, so that we really are not only able to translate it into say masters or PhD projects, but also are able to put it into classroom, our conventional classroom teaching as and when required. So with this goal, I would be starting. So as I said, bolometer was invented by Samuel Langley, and it is a device that changes temperature when it absorbs the energy of a particle or radiation in general. So temperature change is usually sensed by measuring a resultant change in electrical resistance in a thermometer that is thermally coupled to the bolometer. So suppose you have a material which we will call the absorber, and radiation is impending on it. So basically, like this radiation could be in the form of photons, could be in the form of microwave radiation, could be infrared radiation, could be even energy deposited by particles in the so-called high energy experiment scenario. So as this radiation falls on the absorber, its temperature rises. So basically, we will have a way to like couple a thermometer to this absorber in a manner that we can study any rise in temperature which results when radiation is falling. And in order to be able to use it as a device, we'll need to couple it to a sink, a heat sink, because we cannot indefinitely allow heat to be deposited. Eventually, we will also need to have this heat get into the heat sink. So heat sink would essentially be a large reservoir which has infinite heat capacity. And this absorber material, in order to make sure that the temperature change corresponding to small changes in heat deposition is large, right? So we will have heat depositions which are going to be very, very small. But then the temperature changes have to be substantial corresponding to that. And therefore, the heat capacity of this absorber has to be low. So this C has to be small, heat capacity has to be small, because the energy that we deposit is small. T has to be large as possible, and therefore heat capacity has to be as small as possible. So this is what is mentioned here. So the energy is absorbed, producing a change in temperature, and therefore it depends on heat capacity of the material. And smaller the C, better is the response. Okay, and so therefore, like what I just mentioned, small heat capacity induces larger temperature change. Incoming flux correspond to relatively small changes in temperature, and hence resistance or voltages. So therefore, thermal noise need to be minimized through cooling. So that is what. So one of the issues would be and all of us would have seen a connection between like noise and heat capacity and temperature, right? So that we will be kind of looking at in due course, maybe when we discuss all the details. So therefore, this thermal conductance G could be obtained via following the recipe as I'm going to mention. So what we need to do is we need to ensure that a small amount of bias power is injected into the bolometer to elevate the temperature T1 slightly above that of the heat sink. So basically what we'll do is the heat sink is going to be at a temperature T0, whereas the bolometer is going to be at a temperature T1. And of course, there is a heat link which is connected to the sink. And this time constant is a function of thermal conductance would be dependent on temperature we are maintaining it and what is.
Professor Thakur, maybe there are small issues in sound.
Am I not audible?
Yeah, sometimes it's
Yes.
okay, but please adjust your microphone, then it will be good.
Okay. Let me see. Hello. Professor
Yes.
Hussain, can you tell me if the sound is proper now?
Now it's okay. Now it's okay. So please. Please continue. It's okay.
Parameter that we will have to worry about is quantity called gamma. Okay. So the parameter that we have to consider now is this quantity thermal time constant tau, which is going to be C. Have been like just to give a barometer. So a radiation budget accurate regional and global measurement of the components of the budget. So if we look at the Langley's bolometer, right, this is the typical image of the Langley's bolometer, and that was composed of two thin strips of metals, a Wheatstone bridge, a battery, and a galvanometer. So Langley's instrument enabled him to study solar irradiance or light rays from sun far into its infrared region and to measure the intensity of solar radiation at various wavelengths. The point to be noted here is even in those times in early 19th century, one could measure 100,000th of a degree C temperature change using such a bolometer. So how can one really enhance sensitivity of these bolometers? So one of the ways is to use sensitive bridges. So let me explain how a bolometer really works. So the material which we are going to use as bolometer will get into this arm. So this is going to be the bolometer arm, and this is a typical Wheatstone bridge arrangement. And we will have other resistances like P in the two arms and T in another arm. And like what we will be doing is, like what one does is trying to couple the current which flows in the along this end. Say if I call this A, B, C, D. So the current along D is going to be coupled to another kind of via transformer arrangement to an external loop, and then like any small change in the resistance of the bolometer that can be detected via looking at the signal output across this terminal, if we call this S prime S. So about S prime S, the signal output is measured. So over here, it is important that this resistance change as a function of temperature has a good slope. So it is important that the slope of variation of resistance with temperature is as high as possible. And that's where superconducting transition was initially proposed way back in 1946 as an interesting way of implementing a bolometer. So here basically what is done is a superconductor goes from a normal state resistance to a superconducting state. So here the value, non-zero value, is primarily due to the limitation of the voltmeter used, the noise level of the voltmeter used by Andrews et al. So this is essentially the zero resistance state. So here there is a large change in resistance which happens from the normal state to the superconducting state, and this is the noise level in their experiment. And what they suggested was, because there is a sharp change in resistance in this range, one can implement it as something called the transition edge detector based bolometer. So this essentially means that there is a superconducting film as one of the arms of a bridge, right? So this becomes, if we look at the case, this becomes the arm CA in the bridge, and then heat is like the radiation is pushed onto it. So basically the radiation is going to be falling on this arm, and other arms are shielded from any radiation. So in such a scenario, because there is a large change of resistance in this temperature range, so of course this requires detector cooling to superconducting temperatures. Right, and then this entire change in resistances could be sensitively measured, and the overall sensitivity of the bolometer could be enhanced. There is some work which came out from our group recently that is based on this colossal Seebeck coefficient in Aurelius phase perovskite oxide composite. So here you can see that this alpha, or which is more commonly the Seebeck coefficient S, that is about 300. So this is about 300 millivolt per Kelvin at room temperature, and like this was achieved via a specially designed or special choice of materials, and I would be coming to that discussion in a while. And because this Seebeck coefficient is so high as 300 millivolt per Kelvin, one can actually end up making a sensitive measurement of temperature changes and like measure the corresponding voltage right? So very small temperatures like 10 raised to minus 7 Kelvin could be easily detected using conventional nanovoltmeters that we have in our laboratories. So therefore, this material had tremendous promise for um, bolometric application. So the reason why this material has a high Seebeck, let me just try to motivate. So over here, you can see the lattice spacing for like lattice spacing, two different lattice spacings like 1.041 nanometer and 0.274 nanometers. So this 1.041 nanometer, this corresponds to the Aurelius phase. And Aurelius phase could be imagined to be stacks of perovskite. So maybe you can take a set of perovskite and a stack of peroxide layers. So this would be like A2, B2, or rather, let me just call it as BO2. Okay. So let me call it B2O2 layer. And these layers are like A, B, 3 of the typical perovskite type layers. So what is being done is a set of say M layers of perovskite and maybe N layers of peroxide can be like stacked up in a naturally stabilized Aurelius phase. So for example, the material that we worked on, SBTO, what was one of the beginning members is a super structure. And is that we are to SRO layer or TIO layer and A2O2 layer. So this was like conducting layers sandwiched between insulating layers of a scenario where kind of 1D wells, 1D potential wells equivalent scenario. So basically, if we look at Seebeck coefficient of thermoelectric materials, which is S or alpha, right? So that has this crucial part, which is d by dE of log, and the sigma A happens to be very large. Like sigma is the density of states, which happens to be extremely large in this 1D well like structure, and that leads to enhancement of Seebeck coefficient in this material. The fact that in this in our problem we have not only used the Aurelius phase, but also we had added to it an LSMO type of a perovskite in addition to the Aurelius phase. It was primarily to make sure that uh, the overall like resistance of the sample reduces. So Aurelius phase by itself has reasonably high resistivity. So in order to make it much more measurable, we added the and made a composite out of this Aurelius phase and perovskites, and that led us to extremely high Seebeck coefficients, which was demonstrated to be of utility for our. So now I would go into some details, because this was also like it was going to be like a classroom talk. So what we are going to do is trying to look at superconductor based bolometers. And what we are going to do is we are going to eventually look at the equivalent circuit of a bolometer based on superconducting transition edge detectors. So one of the important parameters is this temperature coefficient of resistance. We'll call this alpha R, right? And alpha R is defined as 1 over R dr dt. So for typical kind of metals, R as a function of temperature is like alpha RT. This goes as alpha RT, like some constant plus alpha RT. So I would say it goes as this. Right. So therefore, I should actually do it slightly differently. I'm sorry, I'm unable to undo this writing. So for metals in general, this resistance goes as like as a function of temperature. It increases with temperature. So therefore, like one can see that whatever is the constant of proportionality, that will happen to be alpha RT, and that's because dr by dt is going to be alpha R, and then this 1 over R is going to be
Sir,
so
R
for
is equal to A
metals.
E power
Okay.
B by T, sir.
Yes, that's right. That's
Capital
right.
R is
So,
equal to A into
like
E
for
power B
metal,
by T. Apply ln on both sides, sir.
no, that is for for semiconductors, right? What you are talking about is for semiconductors. You are right. That is for
Then with what?
semiconductors. Okay, so what we are talking about is R is electrical resistance, and this is going to be directly proportional to temperature, right? So for metals, one can see that alpha R is going to be like 1 over T. So why? Because say suppose this resistance, I accidentally used the same symbol alpha R here, which is not really true. So basically resistance of a metal will go as something like some constant plus some other constant times temperature, and therefore like if you take a first derivative with temperature, so this is going to lead us to C1, and when you divide it by C0 C0 plus C1 of T, right? So then this is going to be the first order term, or the leading order behavior is going to be 1 over T for metals. And similarly for semiconductors, this alpha R is going to be about some constant divided by T square, and this is negative. And this is where what you just now said, like the resistance for a semiconductor is going to go as exponential some band gap by temperature, and that would lead to an alpha R, which is like minus A over T square. So hold on, we'll come back to these two later. So now for certain metals, the superconducting transition, although not discontinuous, shows a very rapid change of resistance with temperature, and therefore like what one is trying to do is try to see how to really look say in the case of superconductors. Delta T is like delta T is what we are interested to see. And if we look at resistance as a function of temperature, where did it go? So what we are really talking about is using a superconducting film in the, so if we say this is TC, in the transition region, right? So basically what will happen is there is a TC onset and there is a TC, say let's call it TC prime. So in this case, like the temperature T is going to lie in the range of TC onset and TC prime, and that's where we are going to anchor the superconducting film. And then whenever radiation impinges onto the superconducting film, its temperature is going to rise, and it is going to rise in this window. So suppose to begin with, if it is at a temperature say T0, then depending on the radiation deposited, the temperature will rise and a corresponding resistance will change. However, for superconductors, it turns out that the current flowing through the superconductor is also a crucial parameter. So if delta T is a temperature change, conventionally delta R should have been this quantity called alpha R delta T, right? Because delta R by R is alpha R delta T. However, for superconductor, metals, if we are considering this is the thing. So for superconductor, this delta R will have two components. So there would be a delta R by delta T plus delta R by delta I. So where I is the electric current passing through
Sir, what is the temperature
bolometer.
range for type 1 and type 2 superconductor, sir?
What is the temperature range for type 1 and type 2? I have not spoken about type 1 and type 2 superconductors, but here, so the crucial thing that differentiates type 1 and type 2 superconductors are these critical fields, right? The fields below which the superconductor would be a perfect diamagnet. So in a type 1 superconductor, there's only a unique critical field Hc, right, below which the superconductor would be a pure diamagnet. Whereas for a type 2 superconductors, there is a lower critical field Hc1 and an upper critical field Hc2. And in that range, magnetic field penetrates to superconductors. But that immediately is not of a concern as far as this derivation goes. So of course, like if we want to know more about it, I can discuss that later. Right. So at the moment, what I was trying to motivate was this change in resistance is not only coming directly from change in temperature, but also is like in these superconductors because of this current flow. Because current flow leads to a so-called critical current effect, like which is relevant in the case of superconducting bolometers. So for the thermal response of the bolometer to an incident heat input dq is going to be some c rate of change of plus g okay, so this is going to be I square r plus is going to be absorptivity related terms, so dq by dt plus delta of vi. So where C is going to be the heat capacity or thermal capacity, so mass is multiplied to it, thermal capacity, T is the temperature of operation. So this would lie between Tc prime and Tc onset. G is the thermal conductance between the bolometer element and the thermal reservoir. So TB is going to be the temperature of reservoir. I is the current through volumeter element. R is the resistance of the bolometer element, and A is the absorptivity for the radiation of the bolometer element, and V is the voltage across volumeter. So this is basically a conservation law through which we have written this, and therefore in equilibrium with no inputs except I, except bias current, this is going to reduce to G Ts minus TB equals to I square R. So where Ts is going to be the bolometer temperature. So the operation temperature, and so if we now consider deviation delta T from equilibrium temperature Ts, right? This is going to be like, we are going to reduce it to like d delta T equals to A. So let me just briefly tell you. So what we are trying to do is trying to come up with an equivalent circuit model, like the kind of things which we develop for other semiconductor components. So similarly, we are trying to develop an equivalent model for that. So delta Vi is going to be, sorry, delta V, delta Vi, delta V, right? Delta V is going to be I delta R plus R delta I, because here even R changes, and delta R, as we saw earlier, was alpha R delta plus some beta R delta I, with, of course, alpha R defined as earlier 1 over R dr by dt, and beta, we can also call this beta R or something. Beta R is 1 over R dou R by dou I. So using this in above, like, we obtained C t by dt of delta t plus g of g minus alpha r of p, where p is now the power delta t equals a dq by dt plus beta r p plus 2v delta I, where p is going to be I square r. So the response delta V to the external input like dq we would like to kind of obtain, and we will define a quantity r which is called responsivity, and that would be delta V divided by dq by dt. So a small heat provided in a small time dt, like what would be the change in voltage because of that. And so now from here we'll try to take up. So I think you will have to look at whatever we have done till now. So we have essentially started with a kind of conservation equation, and over there we have put in this dependence of delta r on alpha r and beta r defined through variation of r with temperature and variation of r with current. And we have written down an expression in terms of power P, which is I square R. And now what we'll do is we will take this delta T to be of the general form, say delta T e to the power I omega T, or e to the power, yeah. So where this, or j omega T, where j is square root of -1. This is required just to like we will see the consequences just now. We'll substitute it in the previous equation, and what will come up with j omega plus g minus alpha r p times delta t.
Professor,
Yes.
kindly explain this equation through experimental graph, Professor. For example, alpha is equal to 1 by r dr by dt. No, what is that unique r?
Right.
What is that unique r?
Unique r.
At what intersection you are finding out the slope? Kindly explain, Professor, that one.
So see, we said alpha r is 1 over r dr by dt, right? This is what we defined. And so therefore, like we had already seen that it purely depends on how r varies as a function of temperature. So this alpha r is going to be crucially dependent on what is the temperature dependence of r.
But
Right,
when
so
you
at the
plotted a
moment,
graph between r and t, you got a straight line, no, Professor. So from
so
the
R and T will not be a straight line for the entire range. So let me proceed, because we will do the graphical analysis soon. We will do towards the end of this class. We will
okay.
do, and I will give you references to where one can read it further. So of
Okay, Prof.
course, like
Okay.
if you want me to like jump few steps, so let me just try to show you what we are really after. So it's a good question which is asked. So I think it deserves to be answered right now. Suppose we are looking at R versus T, right? We know that at small temperature, there is an initial rise, then there is a straight line dependence, and then again a kind of, so the slope changes in this specific region, right, and this specific region, and in between it's a linear dependence. So therefore, if we are looking at dou r by dou t, so that is going to have a situation where in this region there is a sharp rise, and in this region there is a sharp fall, right? And in between there is a scenario where the slope is going to be constant, right? So that is how dr by dt is going to look like. And if we are trying to look at the next derivative, d2r dt2, so that is going to look like, so in this region now, because it has gone up and uh, again become like constant, so again the slope goes to 0. So initially slope is 0, and at the end slope is 0. So therefore, what we'll see is a spike like this here, and corresponding to this, there would be a spike like this. So that is what we are going to see, right? In a similar manner, if we are trying to look at d2r by like dr by di, so dr by di will also have a similar dependence with a different scale, of course. So dou r by dou I would also look very similar to this, and a quantity like dou 2r by dou I dou t is also going to look like what is the situation for dou 2r dou t2. So is that fine? This is how the graphical dependencies of r with temperature, partial derivative of r with temperature as a function of temperature. So this is temperature axis, like for all of them. Yeah, so this is what I wanted to like respond in response to the question. Yeah. So what I was trying to derive was this dependence on like Cj omega plus g minus alpha r p of delta t, that is going to be equal to, now this is like beta r p plus 2v delta I plus a dq by dt. So like basically using this equation in the equation which we had written initially for c d delta t by dt, and the previous one which is g ts minus tb equals to I square r. Right, so let's just label these equations, that would help. So let's call this equation 1. This is 2. This is 3. And this together, let's call it as equation 4. This is 5. This is 6. Yeah, and we should also number this as 4a. So these two equations, let's call it 4a and b. So that's equation 4 only, and this is 4a, 4b. So what we are trying to do is trying to substitute the latest expression that we obtained into So we will have an expression for 4. Yeah. So use this in 4 and 4A and B. We are going to come to the expression which is going to look like, we are just 2 more equations away before we can talk in terms of impedances. Minus of IR by A alpha P times G plus Cj omega plus alpha P delta I by delta V, and that is going to be equal to 1 over R, that is dq by dt by delta V, which is R inverse. So what we have essentially done is obtained this expression for R inverse in terms of rest of the parameters. You have to understand that there is a first term and then the second term is IR by A alpha P multiplied by this whole expression. Okay, so here if we now use the incremental variable, so basically using dV by di as equal to minus 1 over z. Let's just label this incremental impedance. Let's call it this as incremental impedance. Then what one can do is one can write this as iota G plus C J omega minus alpha P divided by alpha R P times A plus IR by ZL times G plus Cj omega plus alpha P plus beta R G plus Cj omega divided by A alpha R P, and this whole thing is going to be R inverse, and therefore like this R omega is going to be equal to dV by dQ by dt. Like this is the responsivity for the bolometer. That's going to be I inverse A alpha R P divided by G minus alpha P G omega C ZL by ZL plus Z. So now from here, like R omega is going to be, so in the situation when ZL equals to R, right, you will have a simplification which is like R omega equals to A alpha R P divided by 2 iota G plus J omega C times 1 plus iota beta by beta R by 2. And in the situation when ZL equals to infinity, this simplifies to R omega is going to be A alpha R P divided by twice I G minus alpha R P plus J omega C. So therefore, like the overall result for R omega, which is now going to be composed of two parts, like where we'll now try to introduce this time constant tau, which was C over G, right? So this was the thermal time constant which we talked of earlier. And if we say IC equals to G over dou R by dou T root under, which we'll call the critical current, then we can write R omega in terms of these tau and IC as A alpha R T 2 iota G 1 plus J omega tau times 1 plus iota beta R by 2. Which is going to be equal to A I divided by 2 IC square 1 plus J omega tau times 1 plus B iota beta R by 2. So we have been able to therefore obtain an expression for the responsivity function for the superconducting bolometer in terms of the usual parameters which are falling in the experiment, and accordingly the bolometer bias circuit could be typically drawn here. So let's just try to do that for a typical scenario. So here there would be a bolometer resistor, and then we are going to have a coil to filter out. So this is the typical geometry which you will have to put the superconducting film in if you want to implement a bolometric experiment in your lab, and it's not very difficult. You have to give a typical voltage of say about 30 volts here, and you have to couple this through a transformer like configuration. And match it up with a ZL equals to R. So in the low frequency, low current limit, the impedance is going to be having a typical functional dependence with temperature, and the existence of and location of the peak in this functional dependence would be found out by temperature derivative of this impedance equated to 0. So there is some more like algebra which is required in between, but I think like just because it's not a blackboard kind of a discussion, it becomes little difficult to engage everyone. Like I'm not able to see all of you while I'm writing, so I'm not sure how effective is this. Like in a classroom like scenario, this would have been much better. So I don't know how much of it I should really cover. So here it is important to like tell you that one important thing is the low frequency, low current limit. Like, and in that scenario, this impedance is going to be R times 1 plus 2I square by IC square plus I dou R by dou I 1 plus I square by IC square. And this is independent of frequency. So therefore, typical like bolometric experiments using superconducting films as the active element or the absorber element is done in this low frequency, low current regime. And so if we are plotting Z against temperature, then like these curves will show an initial rise and then a decrease, just as we plotted during this class. And like the existence of a location of this peak could be found out by doing a d by dt of z omega equals to 0, and that would lead us to an expression which will be like dou r by dou t 1 plus 2i square by g dou r by dou t. I square by g dou r by dou t. Equals to 0, and this equation can be satisfied if either d2r dt2 or d2r di dt is sufficiently small, or like it's kind of less than 0. So all other quantities are greater than 0, right? So therefore, basically what we are trying to look at is so here it is important that uh, the effect due to like transition is to be larger than the effect due to thermal effects like temperature, and that leads to a criteria just by looking at this previous expression, which says dou r by dou t has to be less than I dou 2r by dou t dou I. So this is one of the criteria which is going to set the operation point for the bolometer at low frequency, low current region. So that is kind of crucial here. So what we are trying to tell you is what I am trying to tell you is the guiding equation is going to be the following for impedance, and the criteria which must be satisfied has to be the following: that the temperature derivative of resistance should be less than current times second derivative of resistance as a function of temperature and current respectively. So till this criteria is satisfied, one can faithfully use this bolometer with linear characteristics. So therefore, that is kind of very important. So in fabricating these kind of bolometers, the steps which are followed are as follows. So, like to begin with, you will have a kind of sapphire substrate, and on top of that, you will be depositing thin films of this like superconductor, and then like so once you can either evaporate it or sputter it or deposit it using laser deposition or e-beam deposition, depending on the nature and type of superconductor that you are using. If it is a single component superconductor, then of course evaporation or e-beam deposition is the best possible technique. Even sputtering works. However, if it is a multi-component superconductor, then either you will have to rely on a reactive sputtering technique, or you can resort to techniques like pulse laser deposition if it is a high TC superconducting thin films. The advantage of high TC superconducting thin films is the transition temperature is much higher, like say 77 Kelvin, above 77 Kelvin. So you can either operate it at liquid nitrogen with liquid nitrogen cooling, or you can enhance the noise performance of these detectors by operating them at much lower temperatures. So that's something which is kind of relevant here. So let me just go to So besides this, like people are also nowadays trying to make these kind of bolometers using a wide variety of 2D materials that people synthesize in lab, including graphene, reduced graphene oxide, or molybdenum sulfide. So the following work by Chiang et al., like that came up recently, and they had come up with a responsivity as high as 8.58 into 10 to the power 5. Like so, like this is one of the record responsivities for bolometers. So this is kind of expected to open floodgates for looking for 2D materials for bolometry applications. So now here I'm just showing some of the typical applications for bolometers which have been done. So EPIC is basically an like a cosmology experiment, cosmology related experiments, and like all these are astronomy cosmology related experiments. So where they have deployed bolometric arrays in Herschel space probe or EPIC space probe or the Planck space probes. So they are expected to capture events from early universe like happenings. So microwave radiation from early universe processes like these bolometers are expected to capture and shed more light on how nature behaves. Fine. So yeah. So I have given a short like tutorial set for this class. So if like people have gotten it, we can go through it once and try to see if like people can answer questions based on. Okay, so let me just see. Yes.
Sir, you have finished?
Yeah, so I would like to just ensure that if there is the tutorial set is available with all of them.
Okay. What we will do, sir, if now participants if has any question, they can ask in the chat box.
Right, sure.
So please, participants, please.
Okay. So, Professor Hussain, I realized that because of this kind of a live offline class would have been much better by actually looking at the audience and understanding which step is being followed or which is not. I tried to make sure that at least some of the details which people need to know when they are trying to develop bolometers using superconducting thin films and try to estimate quantities like responsivity. That is done in detail.
Yes, yes, yes.
Otherwise, only pictures would not have been very useful. And this transcripted slide, like where it's all these annotations are present, so that I would be sending to you. This can be circulated to the participants.
Yes, yes, yes.
Professor, Professor,
Yes.
I want to just know, Professor, that you wrote that alpha is equal to 1 by r dr by dt. No, what is that r? In that graph, I want that unique r.
In graph, you want the unique R. Okay, let us
Because
see where did we
from
plot.
that graph only we plot, no, what is that r?
Huh.
1 by r
So,
dr by dt, plot, no?
So, okay, exactly. So what you are saying is, like you are worried about in which range we should operate it. So I already told you there are two criterias which must be satisfied. One is when we are operating this device in low frequency, low current limit, we have an expression which has to be obeyed, and we also have to ensure that dou r by dou t is less than I d2r dou t dou I. So that typically is very conveniently found out. So suppose if you have a R versus temperature dependence. So we see that in the superconducting state resistance is zero, but as it like starts getting into the normal state, there is a non-linear variation, right? And then there is a linear regime. Okay, and then again there is a non-linear variation. So what one tries to do is try to restrict one's operation of the bolometer in this linear regime. Okay, so in this linear regime, you can see that this R would be given as some constant times temperature, right? So you know that dr by dt is equals to this constant itself, and therefore 1 over r dr by dt is like 1 over ct times c, which is 1 over t. So this is very similar to what we saw in the case of metals when we wrote down. So in the case of metals, this was supposed to be 1 over r, yeah, 1 over t. Right, so the leading order behavior has to be 1 over t here. So in the case of superconductors also, that is satisfied if we stick to the linear region of the transition regime. Is that clear now? I understand that's why you were kind of asking that where we are choosing this R.
Yeah. Because in semiconductor we have a curve and that there is intersection of the line.
So in semiconductors, that alpha R would be having a more complicated temperature dependence. Like it is typically minus 1 over, means minus some constant over t square.
Hello, sir.
Yes.
Hello.
Hello.
I am Dr. Jitumani Kolita from Cotton University.
Yes. Hello.
Of this book or some references where. Hello.
Yes. I'm telling you. Just hold on. Thanks for raising this question. Hello. Yeah. Thanks for raising this question. Hello. I can hear you.
Yes. I wish. I wish to know the reference of the book.
Okay. So I can tell you. I can help you with that. So one of these initial papers which was written, in this area was by I think M.K. Mall and M.W.P. Strandberg. And this is a Journal of Applied Physics paper, and 42822 1969. Hello.
Yes.
It's an old paper. However, there is another interesting paper which would be APL 801838, of 2002. In fact, there is a lot of scope of these kind of developmental work if we are thinking about research experiments on board ISRO spacecrafts. Like so, in near future, when ISRO decides to do some of these kind of experiments in more detail, right? So we cannot borrow technology from abroad straightforwardly. So a lot of these things have to be developed in-house. And in fact, a lot of developmental work goes on in various universities and like across the country, including IITs, ISC, TIFR. So like, so this is an interesting area where, say, even with liquid nitrogen, one can think about making interesting like bolometric devices and characterizing them properly and developing a product out of them. So that is really a fruitful venture.
Okay, thank you very much for the reference and for your nice presentation. We followed you and it was nice. Okay, thank you. Thank you so much.
So any more question? Okay, so what I will do, I will share the video of Professor Thakur's presentations in the WhatsApp group later. And also if sir give me some handout or whatever maybe sir mentioned, I will share it with you all.
Yes, yes,
okay.
Yes.
And one thing, Professor Thakur, I want to mention, your you see, very rigorous board work reminded me our student days. It was very nice. So normally people what they do, normally we show some image and this kind attractive kind of things only. Hardly we go for basic or rigorous this kind of things. So it was very nice and you have done a lot of hard work. So I thank you very much.
No,
Sir,
I think
please.
I'm missing out something here. Like if I would have been in a classroom-like scenario, then this
Yes,
interaction would have been more lively,
yes,
and
yes.
I would have followed straight away if things are completely lost, and maybe had given some handout in advance. I think that is something which could have improved the
Yeah,
overall
maybe.
efficacy. Yeah.
Anyway, overall it was very nice and quite different. So I enjoyed this one very much, and I thank you for your effort. And we are grateful that you are associated with our department, and in near future also, we will. I am sure that we will have your cooperation. So thank you very much, sir.
Okay.
And
Thank you.
if you share anything regarding your lecture, I will share it with the students.
Yeah, sure. I will do
So
that.
thank you very much, sir.
Thank you.
So there is announcement for the participants. Today we are almost end of the program, and this was the last session. So now the test link is open and it will remain active till 3:45 or till 4 o'clock. So please submit your test response by 4 o'clock. After 4 o'clock, the link will be deactive. Okay. And tomorrow, our first session will start at 10 o'clock. So please join with us at 9:45, by 9:45, and our link will open at 9:30. So hope you have enjoyed. Till tomorrow, goodbye. Thank you for your cooperation, presence, and support. Thank you very much.
Thank you.
Thank you, sir. Thank you. Shall we leave, sir?